To start with atmospheric dynamics, we first derive the non-rotating atmospheric equation. For the equation, we note that the three fundamental forces affecting air in the atmosphere are the pressure gradient force, the frictional force, otherwise known as the viscous force, and gravity. For the pressure gradient force, we imagine a infinitesimally small box with side length delta x, delta y, and delta z, which are extremely small distances. And what we do is we shrink these distances through a limiting process until they become a point-like process, point-like box. And we cannot, unfortunately, as humans, we're not able to reach this point of infinitely small, so we can use calculus to get a approximation of that point. So, for pressure, we first note that by definition, pressure is equal to the force over a certain area, A. And in this case, we'll have pressure in the x direction, pressure in the y direction, and pressure in the z direction. And so for the derivation, we'll focus on the x direction. So we have in the x direction, the area we're looking at is the area of this wall here that the x direction is going through, that the x direction is normal to, which means it's perpendicular to that wall. And we'll call this right wall wall A and the left wall wall B. And so by definition of force is equal to mass times acceleration, we have that the acceleration of pressure in the x direction is equal to the force in the x direction divided by mass, and the force in the x direction is the sum of the pressure force through wall A and the pressure force through wall B. And since F is equal to pressure times A, because we can move the A to the left-hand side, we now get that pressure on the A face in the x direction plus pressure on the B face in the x direction times the area, which is delta y times delta z, these two sides. We have this, and we also can expand these pressure terms using the Taylor series expansion, which is a series of the initial pressure plus combinations of the derivatives, double derivatives, up to the infinite derivative. And of course we can never get there, so we can stop and approximate the Taylor series after the first or second term. And it turns out that this equation, even if we were to expand out the Taylor series, it's going to cancel out in the exact same way every single time. So we will end up with a pressure gradient force that is a perfect representation of this derivative. So for the A face, we have a negative contribution because it's in the negative direction, and a positive contribution for the B face. And we have P naught plus partial P partial X, delta X over 2, and times our area. And then the same thing here, except we have a minus sign here. And if anyone knows why there's a minus sign, you can answer in the comments. I am actually not quite too sure. and of course we still kept m. And so to combine these terms, we'll end up getting negative of partial p partial x delta x over 2 minus partial p partial x delta x over 2, and that will end up what it'll give us is hold on, the minus applies, minus this term will actually be a plus, so we'll get a minus 2 because these terms add up together of this partial p partial x times delta x over 2. The 2's cross out, and we're left with this negative delta p delta x, and we forgot to include the area, so let me do that. Delta y delta z delta y delta z, and we're left with, yes, the delta x is still here, and so we can take that out. We have partial p partial x times delta x delta y delta z, and hey, that's just volume. So for acceleration of the pressure gradient force in the x direction, we have its negative delta x delta y delta z, and I apologize, these are actually deltas, delta, 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 over m times w delta x, and that will be negative volume over mass times partial p partial x, and we know that rho is equal to m over v, so this is equal to 1 over rho. So we'll have negative 1 over rho partial p partial x, and if we do it in the y direction, we'll get the same thing except it's partial y. In the z direction, we'll get the same thing except it's partial z, and each of these rows are for a specific direction. This is for the x direction, which we denote with the unit vector I hat, and this equation will be in the y direction, so j hat, and this will be in the z direction, so k hat. And in calculus, we have an operator called the gradient operator, which is equal to, it's an operator that applies to something. It's basically the x, y, and z components. So for example, if we get the gradient of p, it will be equal to p I hat plus p j hat plus p k hat. So we basically insert a p here. It means you insert a p in every term here, or multiplying a p and then distributing it to each term. And so as you see, this is exactly what this equation is. We can write it as negative 1 over rho times the gradient of p. So you can also think of it in this way, using Newton's law, that the sum of the accelerations of all pressure gradient, the vector form of these equations, is equal to the let me think about this to make sure it's correct. This will be APX, APY, APC. I think it's better just to ignore this part. So the calculus the calculus definition that we just discussed. So we can ignore all this. we know these are all, we're trying to combine them into this vector acceleration p of pressure gradient, and using this we can get that it's -1/rho times gradient of p. And from thermodynamics we can also write this as alpha, the specific volume, to make it more simple, kind of get rid of this fraction. Just a neat trick for doing that. Okay, now we move on to the frictional force, otherwise known as viscous force. So this one is a bit more complicated, but in essence it's the same method. So in this case we imagine the air rubbing against other air. So you can think of it like you have your point and there's some air on each side of it that's having some sort of effect. And so we can think of the x direction, which will be notated on the right side. We have that this tau is known as the shear. So like shear basically means two planes that are like rubbing against each other. Like maybe you take two loaves of slices of bread and rub them against each other. That force between them is tau. So we have that tau along the z face in the x direction. So the z face will be this face here. And the way we define the faces is we say that, if the z direction is this direction, the face parallel to it is this face. And then if you think the x direction kind of parallel to that motion is this face. And then for the y direction, it's a little bit counterintuitive. So I guess that's just the way that I remember it. But this is the y face. So along the z face for the x direction, we also have along the z face for the y direction, and along the z face for the z direction. And so for the x direction, if we make this direction x and this z, so kind of looking this way, the z face will be on either side of it. And same for y, it would be going into the page and there'd be some friction here. And then for z along z, it will be moving up and there'd be some z friction right along with it as well. And each of these times, because they're all along the z face, they all have the same area, which is again delta y delta z, delta y delta z, delta y delta z for all those cases. And applying the same thing that we did before, the acceleration along the z face in the x direction, the vertical shear, is equal to this term divided by m, and we end up getting volume over m, which is 1/rho, and then we get this d tau zx partial z term, and we know through other derivations that tau zx can be defined as mu times the partial u over partial z, so how u changes in the z direction. And mu is the viscosity. So you can think of this as it's a constant that can actually be changing be different in different locations. But you can think of it like honey. Honey has a very high viscosity, and that's why it kind of takes so long to drip, while water has a very low viscosity and might fall very quickly. And it kind of affects how strong the friction is. And so we can then get that we have 1/rho by plugging this in. 1/rho partial z times this mu partial u partial z. And if we assume that mu is a constant, it's not different, it's the same everywhere, you can just take it out and you'll be left with this. However, if you want to be more accurate, this is a truly accurate version. However, mu is very hard to calculate for real situations such as air in the atmosphere. So usually we have this calculated constant value, and for the most part it's pretty accurate. And that will give us a double derivative u over partial z squared. And doing this 6 times, 1, 2, 3, 4, 5, 6, or 7, 8, 9 times actually, 3 times per direction. So this would actually, this here would actually be this column here. And you'll end up getting mu over rho times double partial derivative of u plus double partial derivative of u in y plus double partial derivative of u in z. Here it's v, x, y, z again. This is also x, y, z again, but then it's w, which is the, I believe I have not explained what u, v, and w are. So u, the vector, is equal to u I plus v j plus w k, where u is basically the velocity in the x direction, v equals the velocity in the y direction, and w equals the velocity in the z direction. And so we also know from vector calculus that we can write this term, which is looks like the gradient squared, but it's really notation for the divergence of the gradient, is equal to this. And we call this the Laplacian. And it's an operator that looks like this, and as you see, this is the form everywhere. Cool. Again, here's what we just discussed about the u vector. So we can actually see that this term here, these terms in the brackets here, is just equal to Laplacian of u. If we were to plug this in, we would get, we would get the Laplacian of u, let me just write this. The Laplacian of u is equal to the Laplacian of little u times I plus the Laplacian of little v times j plus the Laplacian of w times k. And as we see, that finally gives us that the acceleration by frictional force is equal to viscosity over density times the Laplacian of u vector. And we could also write it in this form if you like. For the final fundamental force, we have gravity, which is basically a force that only has effect in the z direction. These other forces have had an effect in all directions, but this one will only have it in the z direction. And so that is why we write k here, because if g was a vector in I, j, and k direction, multiplying k inside, we would get ik, which is just equal to 0. And because the coordinate system is set up like I, y direction, x direction, z direction, all perpendicular, also jk would be equal to 0. And finally we get the k times k, which is equal to 1. So that would just leave us with gravity in the z direction only. And so we can take this acceleration as force divided by mass, force of gravity divided by mass, and this is defined, I forgot who, the name of the researcher who found this, but very famous researcher, I'm sure you would know the name if you heard it, came up with this. It's basically the gravitational constant g times the mass of our system, which is, the mass of whatever planet we're on, which is Earth, and divided by the radius of that planetoid. And we can see the calculation here. It's this is g, this is mass of the Earth in kilograms, and this is the radius squared in meters. And we're left with meters per second squared, so meters per second squared. And the math comes out, if you were to keep 4 decimal places, the mass comes out to 9.82. And you might be looking at this like, what? I thought it was 9.81. Well, if you were to limit it to just 2 decimal places, so 6.67 and 5.97 and 6.37, 6.37 squared, you would get 9.81. Something closer to 9.81. However, I think a more accurate reason why it's 9.81 is because gravity on Earth actually changes with altitude and topography. So maybe as you're closer to some sort of big gigantic mountain, such as one under the ocean, you might have higher gravity. In fact, you may even have gravity in the x and y direction in that case, as particles might be more attracted to the mountain in the x direction. But for the most part, this has such a small effect on global prediction of the weather, and it's basically negligible to even care about the variation of gravity with altitude. So we can pretty much use 9.81, 9.82. It won't really have an effect. Now, I personally am of the belief that if we're dealing with things on the micro scale, like 10 to the negative 6 and smaller, like some rain droplets or something, that this term should definitely be expanded to just as many decimal points. And if there really is a region that's affected by large changes in gravity, then those should be taken into account. But I do agree that for the most part it doesn't really matter. So finally, we use Newton's law, which says that acceleration is equal to force divided by mass, which is equal to the sum of all forces. So if you have 2 people pushing on some block, if you have one person pushing, they have a force, and another person pushing in the same direction with another force, those forces are additive. So as long as they're in the same exact direction. So we have that du dt, which is the definition of acceleration, is the derivative of velocity, is equal to the sum of all forces divided by mass. And we already accounted for mass in all these equations. We had divided by mass, so that's already taken care of. So each time we can just, we can also, write this as the sum of all accelerations. So make that blue. And we can just combine these 3 forces that we just found. The pressure gradient, just as in the form we saw before, the gravitational force, and the frictional force. And I'm pretty sure that this term is positive, but hopefully I didn't make a mistake there. And so now for the next video, I will have to discuss a rotating Earth, because these three forces are the fundamental forces that affect air. However, when we're on this rotating system, there are these apparent forces or imaginary forces that appear, which are only due to the perspective of the viewer. So if you set a camera that's on the Earth, as the Earth is rotating, it's rotating and staying fixed in one place. If that happens, air will tend to be deflected from its view as it's standing there. However, if it was standing in space, as the Earth is rotating away from it, and the viewer is not moving at all while the Earth rotates away, it would see the air moving in a perfectly straight line according to the pressure gradient force and the frictional force. The pressure gradient is the main one. However, obviously this isn't a good way of doing things, because as soon as the Earth rotates away from the viewer, you can't see that area anymore. And so it's more useful for us to look at as if we're on the rotating Earth rather than being in a what's called an inertial frame, or a non-rotating frame of reference. So in the next video we'll add the rotation, and we'll see that adds 2 extra terms to this equation here. So hopefully you can look forward to that next video, and stay tuned.